Welcome friends. We will continue with our discussion on differential geometry. In this session, we will see structural equations and curvature. Structural equations and curvature. Definition. Consider the circle bundle S of M of a smooth oriented Riemannian 2 manifold M. Two smooth one-forms omega 1 and omega 2 are defined of Sm as follows. For t element of Sm comma Mv, omega 1 of t is equal to the scalar product of d pi t comma v, and omega 2 of t is equal to the scalar product of d pi t comma iv, where iv is equal to e raised to I pi by 2 into v is the image of v under rotation through an angle of pi by 2 in t of m comma small m. We shall show later in this session that these one-forms are indeed smooth. Note 1. Thus omega 1 of t and omega 2 of t are the components of d pi t relative to the orthonormal basis set v comma iv for t of m comma m, that is d pi of t is equal to omega 1 t into v plus omega 2 t into iv. Note 2. Suppose k is a connection on S of m with connection one form phi. Then the set phi comma omega 1 comma omega 2 is a basis for t star S of m comma mv for each mv element of S of m. Note 3. Let g equal to e raised to minus I theta element of S1. Then g star omega 1 is equal to cos theta into omega 1 plus sin theta into omega 2, and g star omega 2 is equal to minus of sin theta omega 1 plus cos theta omega 2. Note 4. G star of omega 1 meet omega 2 is equal to omega 1 meet omega 2 for all g equal to e raised to I theta element of S1. For g star omega 1 meet omega 2 is equal to g star omega 1 meet g star omega 2, which is equal to cos square theta plus sin square theta into omega 1 meet omega 2, which is equal to omega 1 meet omega 2. Furthermore, omega 1 meet omega 2 of t1 t2 is equal to 0 if either t1 or t2 is vertical. Hence, as in the proof that phi minus phi 1 is equal to pi star tau for some tau which we have discussed in the previous session, the two form omega 1 meet omega 2 is the image under pi star of a unique form on M. Definition. The volume element of a smooth oriented Riemannian 2 manifold M is the smooth two form volume on M such that pi star volume is equal to omega 1 meet omega 2. That is, for v1 comma v2 element of t of m comma m, volume of v1 v2 is equal to omega 1 meet omega 2 at mv v1 dash v2 dash for any mv element of pi inverse m subset of S of m and v1 dash v2 dash element of t of Sm comma mv, such that d pi of vi dash is equal to vi for I equal to 1 comma 2. Note 5. Suppose U is a coordinate neighborhood in M with coordinate functions x1 comma x2. Let E1 equal to dou by dou x1 by norm dou by dou x1, and let omega 1 dash and omega 2 dash be smooth one forms on U such that at each m element of U form the basis for t star m comma m dual to the set E1 of m comma I into E1 of m. Let C from U to pi inverse U subset of S of m be given by C of m is equal to the pair m comma E1 of m. Then for V element of t of m comma m, C star omega 1 of V is equal to omega 1 dc of V, which is equal to the scalar product d pi composite dc of V comma E1, which is equal to the scalar product v comma E1, which is equal to omega 1 dash of v. So omega 1 dash is equal to c star omega 1. Similarly, omega 2 dash is equal to c star omega 2. In particular, omega 1 dash meet omega 2 dash is equal to c star omega 1 meet c star omega 2, which is equal to c star composite pi star of volume, which is equal to pi o c star volume. So since pi o c is equal to the identity function on U, volume at U is equal to omega 1 dash meet omega 2 dash. Now let omega I tilde pi star omega I dash for I equal to 1 comma 2. Then omega 1 tilde and omega 2 tilde are smooth one forms on pi inverse U subset of S of m, and omega 1 tilde meet omega 2 tilde is equal to pi star omega 1 dash meet pi star omega 2 dash, which is equal to pi star omega 1 dash meet omega 2 dash, which is equal to pi star volume, which is equal to omega 1 meet omega 2. Moreover, at each point m comma even m of C of u, omega I is equal to omega I tilde. For if t is an element of t of Sm comma m even, omega 1 t even plus omega 2 t I even is equal to d pi t, which is equal to omega 1 dash d pi t even plus omega 2 dash d pi t I even, which is equal to omega 1 tilde of t even plus omega 2 tilde of t I even. Note further that for g equal to e raised to I theta element of S1, g star omega 1 tilde is equal to g star composite pi star omega I dash, which is equal to pi star omega I dash, which is equal to omega I double tilde. Thus, from note 3, which we have just mentioned, g star omega 1 at m even is equal to cos theta into omega 1 plus sin theta into omega 2 at m even, which is equal to cos theta omega 1 tilde plus sin theta omega 2 tilde at m even, which is equal to cos theta g star omega 1 tilde plus sin theta g star omega 2 tilde at m even. Applying g inverse star, the forms omega 1 and omega 2 at m comma g even are related by omega 1 is equal to cos theta into omega 1 tilde plus sin theta into omega 2 tilde. Similarly, omega 2 is equal to minus sin theta omega 1 tilde plus cos theta omega 2 tilde. In particular, these formulae shows that omega 1 and omega 2 are smooth. Note 6. For higher dimensional Riemannian manifolds, the volume element is obtained similarly. If U is a coordinate neighborhood in the oriented Riemannian manifold M with coordinate functions x1, x2, etc. xn such that dx1 meet etc. meet dxn gives the orientation of U, consider the vector fields dou by dou x1 etc. dou by dou xn. Using the Gram-Schmidt orthogonalization process, we obtain smooth vector fields E1, E2, etc. En on U, which form an orthonormal basis for the tangent space at each point. Let omega 1 dash etc. omega n dash be the dual one forms. Then the n form volume at U is equal to omega 1 dash join etc. join omega n dash is independent of the oriented coordinate system on U and thus defines a global non-zero n form volume. Cartan structural equations. Given an oriented Riemannian 2 manifold M and a connection on S of M with connection one form phi, the one forms phi comma omega 1 comma omega 2 form a basis for the cotangent space at each point of S of M. Hence, the two forms omega 1 meet omega 2 comma omega 1 meet phi comma omega 2 meet phi form a basis for the two forms at each point of S of M. Hence, d phi d omega 1 d omega 2 can be expressed in terms of this basis. The resulting formulae are called the Cartan structural equations. We now derive them beginning with the second structural equation. Second structural equation. On pi inverse u for a coordinate neighborhood u, let phi 1 denote the connection 1 form of the special connection k1. Then d phi 1 is equal to 0, so that d phi is equal to d phi minus d phi 1, which is equal to d of phi minus phi 1, which is equal to d of pi star tau, which is equal to pi star d tau, for some smooth one form tau on U. Now d tau is a two form on U, hence it is a multiple of the volume element, that is d tau is equal to minus k into volume for some smooth function k on U. Thus d phi is equal to pi star into minus k volume, which is equal to pi star volume, or d phi is equal to minus k composite pi omega 1 meet omega 2. The smooth function k is independent of the coordinates used, since it is determined by this last formula. Thus k is a smooth function on M called the curvature of the connection phi. First structural equation. On pi inverse u for a coordinate neighborhood U, we have seen that at e raised to I theta c of m, omega 1 is equal to cos theta omega 1 tilde plus sin theta omega 2 tilde, and omega 2 is equal to minus sin theta omega 1 tilde plus cos theta omega 2 tilde. Now d omega I tilde is equal to d pi star omega I dash, which is equal to pi star d omega I dash is equal to pi into ai volume, which is equal to ai composite pi omega 1 meet omega 2 for some smooth function ai on U. Thus setting ai tilde is equal to ai composite pi d omega 1 is equal to minus sin theta d theta meet omega 1 tilde plus cos theta a1 tilde omega 1 meet omega 2 plus cos theta d theta meet omega 2 tilde plus sin theta a2 tilde omega 1 meet omega 2, which is equal to d theta meet omega 2 plus a1 tilde cos theta plus a2 tilde sin theta omega 1 meet omega 2. If k is a special connection k1 on pi inverse u, then phi 1 is equal to d theta. Thus for this special connection, d omega 1 is equal to phi 1 meet omega 2 plus b1 omega 1 meet omega 2 for some smooth function b1 on pi inverse of u. Similarly, d omega 2 is equal to minus phi 1 meet omega 1 plus b2 omega 1 meet omega 2 for an arbitrary connection form phi 1 minus phi is equal to pi star tau for some smooth one form tau is equal to c1 omega 1 dash plus c2 omega 2 dash on u. Hence, phi 1 minus phi is equal to pi star c1 omega 1 dash plus c2 omega 2 dash, which is equal to c1 composite pi omega 1 tilde plus c2 composite pi omega 2 tilde, which is equal to f1 omega 1 plus f2 omega 2 for some smooth function f1 and f2 on pi inverse u, since omega 1 tilde omega 2 tilde span the same space at each point as omega 1 omega 2. Thus phi 1 is equal to phi plus f1 omega 1 plus f2 omega 2, and by substituting it to the previous equation, d omega 1 is equal to phi meet omega 2 plus f1 omega 1 meet omega 2 plus b1 omega 1 meet omega 2, which is equal to phi meet omega 2 plus f1 plus b1 omega 1 meet omega 2. This together with the corresponding equation for d omega 2 gives the first structural equations. D omega 1 is equal to phi meet omega 2 plus h1 omega 1 meet omega 2, and d omega 2 is equal to minus phi meet omega 1 plus h2 omega 1 meet omega 2, where h1 h2 are smooth functions on S of m. Note that although these equations were derived over a coordinate neighborhood, they are independent of coordinates, thus they are valid globally. Although one might expect that by choosing an appropriate connection phi on Sm, the coefficients of d omega I relative to the basis phi meet omega 1, phi meet omega 2, omega 1 meet omega 2 could be prescribed fairly arbitrarily, this is not the case. In fact, d omega 1 never has a component in phi meet omega 1 direction. Moreover, the components of d omega 1 and d omega 2 never has a component in the phi meet omega 2 and phi meet omega 1 directions respectively, must always be plus 1 and minus 1. It is natural to ask whether the first structural equations can be made simpler by an appropriate choice of connection on S of m. In particular, can phi be chosen such that h1 is identically equal to 0 and h2 is identically equal to 0? The answer is yes, and the choice is unique. This is given as the coming theorem. Theorem statement: let M be an oriented Riemannian 2 manifold, then there exists a unique connection psi on S of m such that d omega 1 is equal to psi meet omega 2 and d omega 2 is equal to minus psi meet omega 1. This connection is called the Riemannian connection. Proof: let phi be any connection on S of m. If psi is any other connection on S of m, then as above, phi minus psi is equal to x1 omega 1 plus x2 omega 2 for some x1 and x2. Solving for phi and substituting in the first structural equations for phi, we obtain d omega 1 is equal to psi meet omega 1 plus h1 plus x1 omega 1 meet omega 2, and d omega 2 is equal to minus psi meet omega 1 plus h2 plus x2 omega 1 meet omega 2. Thus, d omega 1 is equal to psi meet omega 2 and d omega 2 is equal to minus psi meet omega 1, if and only if x1 is equal to minus h1 and x2 is equal to minus h2. This gives both existence and uniqueness. The Cartan's structural equations have a dual formation in terms of vector fields. Let V, E1, E2 be the smooth vector fields on S of M that form the dual basis to phi omega 1 omega 2. Then E1 and E2 are horizontal at each point, since phi of E1 is equal to phi of E2 is equal to 0. Moreover, d pi E1 of mv is equal to omega 1 E1v plus omega 2 E1 IV, which is equal to V. So E1 m comma V is the unique horizontal vector at mv whose image under d pi is V. Similarly, d pi E2 mv is equal to IV. The structural equations then become box V E1 is equal to E2 and box V E2 is equal to minus E1 and box E1 E2 is equal to k composite pi V minus H1 E1 minus H2 E2. If phi is equal to psi, the one form of the Riemannian connection, the last boxed equation reduces to box E1 E2 is equal to k composite pi into V. To verify these equations, apply the formula d tau of V1 V2 is equal to half V1 tau V2 minus V2 tau V1 minus tau box V1 V2 9 times as tau runs through the set phi comma omega 1 comma omega 2 and V1 V2 runs through the set V comma E1 comma E2. Note that if k is a constant, these formulae shows that the set V E1 E2 spans a finite dimensional Lie algebra. From now on, for an oriented Riemannian 2 manifold M, let the connection chosen be the Riemannian connection and let k be the curvature function for that connection. Interpretation of curvature. We now show that the curvature k of M measures the amount of rotation obtained in parallel translating vectors around small closed curves in M. The intuitive reason is this. On Sm, we have the vector fields E1, E2 and V, and we know that for the Riemannian connection, box E1, E2 is equal to k composite pi V, but box E1, E2 of MV is just the tangent vector to the curve through MV obtained by following the integral curves of E1 and E2 forward and then backward through parameter distances of root S. We can see this in figure 1. Projecting this figure down to M, we obtain a rectangular shaped figure which is nearly closed. That is, the curve obtained through M has 0 tangent vector at M because it is the projection of box E1, E2 of MV, which is vertical. We can see this in figure 2. Now the integral curves in Sm are the horizontal lifts of the curves in M. That is, these curves are obtained by parallel translating V around the curves in M. The endpoints of the curve through MV dotted in figure 3 essentially differ by an element S1, namely the rotation g equal to e raised to I theta, which sends V into its parallel translate around the rectangle in M. Since the area of the rectangle in M is approximately root S into root S, which is equal to S, the limit as S tends to 0 of the angle of rotation theta divided by the area of the rectangle is equal to the coefficient of V, namely k of M. Stated precisely and in somewhat greater generality, the result we have been discussing is the theorem given. Theorem 1. Let M be an oriented Riemannian 2 manifold, let S be an oriented 2 simplex in R2, and let H from S to M be a map which has a smooth extension mapping a neighborhood of S into M. Let alpha be the closed broken C infinity curve in M obtained by restricting H to dou of S. Then the rotation obtained by parallel translation around the closed curve alpha is e raised to I integral over S H star k volume, so that the angle of rotation is integral over S H star k volume. Note that this result contains the result discussed earlier. To obtain k of M, take the limit of integral over S H star k volume by integral over S H star volume as S shrinks to 0 and H of S shrinks to M. However, the theorem says more. For example, it is possible to have k greater than 0 on Hs and still get a trivial rotation upon parallel translating around alpha, namely when the total angle of rotation integral over S H star k volume is an integer multiple of 2 pi. Now let us see the proof of theorem 1. Let S is equal to V0 V1 V2 for some vertices V0 V1 V2, and let omega naught element of T of M comma H V0 be the unit vector. The lines in set S through V1 cover S and their images under H are curves in M which cover H of S. Let h tilde from S to S of m be obtained by mapping each of these curves into its horizontal lift in Sm through hv1 comma omega 1 element of S of m, where omega 1 is the parallel translate of omega naught along the curve alpha at scalar product v0 v1 to hv1. We can see this in figure 4. By construction, pi composite h tilde is equal to h. Moreover, h tilde has a smooth extension mapping a neighborhood of S into Sm. This may be checked via local coordinates. Now, integral over S h star k volume is equal to integral over S pi composite h tilde star k volume, which is equal to integral over S h tilde star pi star k volume, which is equal to integral over S h tilde star k composite pi omega 1 meet omega 2, which is equal to minus of integral over S h tilde star d phi, which is the second structural equation, which is equal to minus integral over S d h tilde star phi, which is equal to minus integral over dou S h tilde star phi by Stokes theorem, which is equal to minus integral over dou S phi d h tilde d by dt into dt, which is equal to minus integral over dou S phi d beta tilde d by dt into dt, where beta tilde is equal to h tilde at dou S. Let alpha tilde denote the horizontal lift of alpha through h tilde of v0 is equal to alpha v0 comma omega naught. Since beta tilde at v0 v1 is equal to h tilde at v0 v1 and beta tilde at v1 v2 is equal to h tilde at v1 v2 are horizontal by construction of h tilde, we have beta tilde at v0 v1 is equal to alpha tilde at v0 v1 and beta tilde at v1 v2 is equal to alpha tilde at v1 v2. By lemma 2, which we have proved in this session on parallel transport and connections, there exists a function f from v0 v1 to r with f of v2 is equal to 0 such that beta tilde of t is equal to e raised to I f t alpha tilde t. But alpha tilde is the horizontal lift of alpha, so that alpha tilde v0 is the parallel translate of omega naught around alpha. On the other hand, beta tilde v0 is equal to omega naught. Hence, e raised to I f v0 is just the rotation mapping the parallel translate of omega naught around alpha into omega naught, that is e raised to minus I f v0 rotates omega naught into its parallel translate around alpha. By the second statement of lemma 2, which we have discussed earlier, phi into d b tilde d by dt is equal to df by dt for t element of v2 v0. Moreover, phi d beta tilde d by dt is equal to 0 on v0 v1 and v1 v2 since beta is horizontal there. Thus, since dou S is equal to v0 v1 plus v1 v2 plus v2 v0, integral over S h star k volume is equal to minus integral over v2 v0 phi d beta tilde d by dt into dt, which is equal to minus integral over v2 v0 df by dt into dt, which is equal to minus f v dot, which is equal to the angle of rotation from omega naught to its parallel translate around alpha. Now, we will see some definitions. Let alpha from closed interval a b to m be a smooth curve. The length L of alpha is the real number I of alpha is equal to integral a to b norm alpha dot t dt. The arc length along alpha is the function s from a b to r given by s of t is equal to integral a to t norm alpha tilde tau d tau. Note that L and s are defined because t goes to norm alpha dot t is continuous. The function s is of class C1, but it is not necessarily smooth because t goes to norm alpha dot t is not necessarily differentiable where alpha dot t is equal to 0. If, however, norm alpha dot t is not equal to 0 for all t, then s is smooth and monotonically increasing. Next definition. A curve alpha from closed interval a b to m is said to be parametrized by arc length if norm alpha dot t is equal to 1 for all t element of closed interval a b. In this case, s of t is equal to t minus a for all t element of a b. Note that given any curve alpha from a b to m with norm alpha t not equal to 0 for all t element of closed interval a b, a new curve alpha 1 from closed interval 0 I alpha to m parametrized by arc length is obtained by setting alpha 1 is equal to alpha composite S inverse, then image of alpha 1 is equal to image of alpha and L of alpha 1 is equal to L of alpha. Also note that the concept of arc length extends to broken C infinity curves alpha since norm alpha dot t is defined at all but a finite number of points. Moving on to next definition. Given any curve alpha from closed interval AB to M parametrized by arc length, a smooth curve alpha dash from closed interval AB to S of M is defined as alpha dash t is equal to the pair alpha t alpha dot t for t element of closed interval AB. Alpha is said to be a geodesic in M if alpha dash is a horizontal lift of alpha through alpha of A alpha dot A element of S of M. Note that if alpha is a geodesic, the parallel translate of alpha dot 0 along alpha to alpha t is just alpha dot t. That is, the tangent to alpha translates into itself, and alpha is a straight line of the surface. To measure how far a curve alpha is being straight, we measure how far alpha dash is from being horizontal. Suppose then alpha is parametrized by arc length, so that alpha dash from closed interval AB to Sm is a curve in S of M. Next definition. The geodesic curvature k alpha t of alpha at t element of closed interval AB is psi d alpha dash d by dt, where psi is the one form of Riemannian connection. Notation: if alpha from closed interval AB to M is broken C infinity curve with alpha dot t not equal to 0 for all t element of closed interval AB, let tau alpha is equal to integral 0 to I alpha k alpha 1 t dt, where alpha 1 is the new curve obtained from alpha by parametrizing by arc length. If M is a smoothly triangulated manifold, then tau can be considered as the one cochain relative to the triangulation. The Gauss-Bonnet Theorem for two simplices. Let M be an oriented Riemannian 2 manifold, let S be an oriented 2 simplex in R2, and let H from S to M be a map which has a smooth non-singular extension mapping a neighborhood of S into M. Let alpha be the closed broken C infinity curve in M obtained by restricting H to dou S. Integral over S H star k volume is equal to minus tau of alpha summation interior angles of H of S minus pi. Now let us summarize what we have learned in this session. We began the session with the definition of smooth one forms and the volume element of a smooth oriented Riemannian 2 manifold. We have seen the Cartan's structural equations. We have seen how the first structural equation can be simplified by the appropriate choice of a connection on S of M. Such a connection which is unique is called the Riemannian connection. We have proved the uniqueness by a theorem. We have shown that the curvature k of M measures the amount of rotation obtained in parallel translating vectors around small closed curves in M. We have defined the length of a smooth curve and have seen its parametrization by arc length, which is a geodesic in M. We have also seen Gauss-Bonnet theorem for two simplices, which is proved as a lemma. We will continue with Gauss-Bonnet theorem in the next session. Now you can try out these problems for a better understanding of the topic. First one. Suppose a surface S subset of R cube contains a straight line gamma subset of S. Show that gamma is a geodesic, that is, a curve whose geodesic curvature vanishes. Second problem. Suppose a curve gamma on a surface S subset of R cube has 0 geodesic curvature. Must gamma be a straight line? Third problem. Show that all the geodesics of LP are closed curves. On L3, find two closed geodesics with different lengths. Fourth one. Find the absolute value of the geodesic curvature of the curve cos t cos theta sin t cos theta sin theta on S2 for any fixed value of theta. These are some books for further reading. First one is the Introduction to Differential Geometry by J. A. Thorpe, Springer Verlag. Second one is the Lecture Notes on Elementary Topology and Geometry by I. M. Singer and J. A. Thorpe, Springer Verlag in 1967. Third one is Elementary Differential Geometry by B. O. Neal, Academic Press 1966. Fourth one, Lectures on Differential Geometry by S. Sternberg, Prentice Hall 1964. Fifth one, Differential and Riemannian Geometry by D. Logwitz, Academic Press 1965. Sixth one is Riemannian Geometry by S. Gallert, D. Herlin and Lafontaine, Springer Verlag 1987. Seventh one, Riemannian Geometry and Geometric Analysis 4th edition by Jürgen Jost, Springer Verlag. Hope you all have enjoyed the session. We'll meet with another topic in another session. Till then, goodbye.